Good afternoon, everyone. My name is Meemansa Sood, and I'm a PhD student in the field of computational life sciences. I'm doing my PhD from Fraunhofer Sky and University of Bonn, Germany. Today, I'm going to talk about assessing the role of digital device technology in Alzheimer's disease using artificial intelligence. First, I will talk about Alzheimer's disease and its progression. Alzheimer's disease progression occurs over several years, and it starts from preclinical stage to a severe dementia stage. In preclinical stage, there are no symptoms visible, but in severe dementia stage, there are symptoms which also affects activities of daily living. This activities of daily living is usually represented by functional impairment. And there are two types of impairment usually in this disease, which is cognitive and functional impairment. And these are prerequisites for differential diagnosis of Alzheimer's and mild cognitive impairment stage. There is also lack of cure in the field of Alzheimer's, and this type of treatment which is available, it's only symptomatic, and this cannot stop progression of the disease. There is a big challenge to identify the disease in an early stage, and also treatments which are available are only moderately effective in the early stages. So we need to detect the disease as early as possible. We need to switch from the scenario of diagnose and treat to predict and preempt. In this context, there has been a lot of research going on in the field of remote monitoring via digital devices. One of the companies, Altoida, has developed an app which tests the functional and cognitive aptitude of a patient via a virtual reality framework. And this app is basically consisting of different tasks. For example, you see on the left-hand side, there is a screenshot from the particular app, and herein the participant is told to keep some objects in the virtual world, and then they need to come back and find these objects. So for example, they need to place 3 objects in the environment, they come back and they find without any distractions or with minimum distraction. This would help the app to measure cognition ability from the patient. The second type of task, as you see from the screen, is a day out task wherein the patient has to perform specific function, or he has to execute a function in a specific manner. For example, here he needs to escape a virtual fire. So he needs to perform steps to do that. And this would measure the executive functioning of the patient. Now, we want to see that how much this particular digital data is related to already existing clinical data, and why we want this digital data to predict the disease early on. So first of all, we want to see that how we can assess the relationships between digital measures and questionnaire-based clinical scores. Secondly, we want to assess the sensitivity of digital measures compared to questionnaire-based clinical scores. So let's first look into how to disentangle the relationships between digital measures and questionnaire-based clinical scores. So now I will talk about our methodology. So first of all, the question arises, why cannot simple correlation analysis do this and explain some kind of a relationship? Because they cannot explain conditional dependencies, which variable will affect which other variable. So this can be done by Bayesian networks, and Bayesian networks can represent causal dependencies between the random variables. Bayesian network structure has also some limitations. They are not computationally efficient always. They are only computationally efficient if the variables are multinomial or Gaussian distributed. And this is not fulfilled in case of clinical data, not always. And this Bayesian network structure learning is also very difficult. It is NP hard problem, and true structure is hardly identifiable in case of large number of variables, which is usually the case of clinical data. For example, genetic data, you have a lot more gene expression values as compared to the number of patients. And this gives rise to our approach, which is called variation autoencoder modular Bayesian network approach. This was also published last year. And this is a very novel approach. Here, instead of using Bayesian network, we are using modular Bayesian network. So what it does, it groups different variables into particular modules. So for example, here you see that there are these nodes which you can think about as features, and they are grouped in different modules. So the features which are in one particular module, they share same parameters and parents and conditional probability distributions. Now we want to see that how the conditional probability is represented of a particular module. This is represented by variation autoencoder, which follows neural network architecture. So but here we are using special type of variation autoencoder, which is heterogeneous incomplete variation autoencoder, because in clinical data we have a lot of heterogeneous data and missing data. Therefore, we use this type of VAE. So here, low dimensional representation of each module is learned via variational autoencoder, and then Bayesian network structure or modular Bayesian network structure is learned from these low dimensional representation of modules. Now we have the trained model, which can show the connections between different modules. We need to assess the fit of the model, and in order to do that, we generate synthetic data. And after generation of synthetic data, we compare the individual variable distributions in real data and synthetic data, and we also compare the correlation structures of real and synthetic data. Then we need to test the robustness and generalizability of results. In order to do that, we develop a bootstrap network structure, and we compare the networks trained on different data sets. So in total, this variational autoencoder modular Bayesian network can model arbitrary distributions. It can drastically reduce the number of parameters and edges compared to the conventional BN, and it can model time series data. So now, now I will look at what we are using in our work. So we are using data from Altoida, and it has three different types of data. It has data from digital tasks, digital cognitive domains, and clinical scores. So digital tasks are, for example, I showed you, it's like object finding in augmented reality, and a task like motor tapping features. Second type of task is digital cognitive domains, which is related to prospective memory. So ability to remember, carry out some intended task in the future, and spatial memory is usually to recognize items that previously appeared in space. And then there are clinical scores, which are questionnaire-based scores, which are here mini-mental state examination, and this is usually pen and paper tests in generally routine, done routine in a routine in clinic. So here we have patients like 150 subjects, and there are almost 670 digital task scores summarized into 9 cognitive domain assessments, and there are subjects like normal MCI and dementia from these 3 stages. So what we do, we apply our Wangman model to Altoida data, and we also have different modules. So each node is a module, and the colors are basically representing features belonging to similar groups. So we could see the connections identified between digital and questionnaire-based assessments. This is a bootstrapped network. Here the number on the edges represent the strength of each connection, meaning the confidence of the 2 nodes. And the higher the confidence here, the higher the strength of the connection. So firstly, I will show you a connection which we found between MMSE language and AR object placement. So what MMSE language is, this is a test related to naming, naming a pencil and a watch, or repeating words, and carry out complex commands like drawing a figure, etc. And it is connected to AR object placement. And this particular task is about placing an object, for example, time taken to find a suitable surface and distance traveled, or how a person can hold the device steady. And this means that AR object placement is conditionally dependent on MMSE language. And here we also show the correlation structure between these two features. Now I will also show some more interesting connections which we saw. We saw connections from MMSE orientation, which means testing orientation to time and place, to AR screen button presses. So this particular test is also a digital measure, which is recording touchscreen data of the button press during AR tests. So for example, how much pressure you applied, how much touch accuracy you have. And this is also a very interesting connection we found, and we represent here the correlation plot as well. Now we also find a connection between MMSE orientation to flexibility. So MMSE memory recall to flexibility. And flexibility is a measure, it's a digital cognitive domain measure, which was extracted from the digital tasks. And flexibility here means ability to switch between thinking about two different concepts. So these are some of the interesting connections we see in network from Altoida data. Now we also want to see similar connections or similar network in Acne, which is an observational longitudinal study. And it has different types of features. It has like mechanisms, for example, inflammatory response, ATP binding. Then it has clinical scores. It has same score like MMSE, which is also present in Altoida. Functional activity questionnaire score, which is also a pen and paper test, but mostly reflecting the activity of daily livings of a patient, for example, making appointments, managing finances, etc. Then it has brain volumes, also CSF measurements, and here patients are almost 1,445 longitudinal time point up to month 36. And we also have patients from these three different stages, normal, MCI, and dementia. Now, in order to see the connections in ADNI to the digital tasks or the digital cognitive domains, we use the VAMBIN, which was trained on Altoida, to predict the digital data in ADNI. And this was done to predict digital tasks and digital cognitive domains. Now, what we see here, we also see a very big network in ADNI, and this is also bootstrap network, but this is just a part of the network. But I will show you some interesting connections which we see. And this particular networks are also could be accessed through this link. So we see a connection from FAQ form to planning. FAQ form is a questionnaire-based assessment, which is dealing with assembling tax records, business affairs, papers, etc. And planning is generally a process of thinking about activities required to achieve a desired goal. So this planning is also a digital measure. Then we see connections from from CSF to planning as well. So this is also a very interesting connection. We see a connection from MMSE memory recall to flexibility, which is a common connection with Altoida. And then there is connection from CSF to complex attention measure, which is also a digital measure, which measure like on what you can give attention to, on what you cannot give attention to. And we also find connection from FAQ travel to flexibility. FAQ travel is also a task which is basically measuring how much you are traveling during every day and all that. So these are quite interesting connections we find in ADNI, and we could also confirm the common connections from Altoida, but we could also find many novel connections, especially with these CSF biomarkers and the functional measurements. Now, the second task is to see that how do we assess the sensitivity of digital measures versus questionnaire-based clinical outcomes. In order to do this, we built a sparse group lasso logistic regression classifier on several features. For example, here I am showing the AUC obtained from tenfold cross-validation when the features were when the classifier was trained on features such as digital cognitive domains, MMSE, group of MMSE and digital cognitive domains, digital tasks, MMSE and digital tasks. And this is the classifier built on Altoida data to classify normal and MCI subjects. To here you see digital tasks are outperforming every other classifier. And also when the classifier is trained on combination of different measurements, then it outperforms the classifier which is trained on individual measurements. And this gives us enough confidence that digital tasks are better performing than other types of measurements. Here we also see that there are feature importances when the classifier trained on MMSE and digital tasks. Although we see that MMSE is coming at the top of the feature importance plot, but the absolute coefficient or the overall feature importances of digital tasks is way higher, as you see here in this plot, as compared to MMSE. And this is usually for AR object finding, motor test durations, motor tapping features. These are all the features which are very, very important in classifying the disease. We also build the classifier on Acne, which is classifying the disease into normal and MCI subjects. And this is the digital cognitive domains plus FAQ plus MMSE classifier. Here we see that there is MMSE is not important in classifying normal and MCI, although FAQs are important, but they are way less important than the digital cognitive domains. And also in the overall feature importances, digital cognitive domains outperform the FAQ and MMSE classifiers. So in order to conclude, what we were able to see, we were able to establish non-trivial relationships between digital and classical questionnaire-based clinical measures, such as FAQ and MMSE. And we propose here a modeling approach. This could help to indirectly connect digital measures with CSF biomarkers, which could be very important in diagnosing the disease at an earlier stage. And digital tasks and digital cognitive domains are more sensitive to classify the subjects at an early stage as compared to the questionnaire-based clinical scores, as we saw here, such as MMSE and FAQ. So in total, we were able to, in conclusion, we were able to basically achieve what we wanted to see here, that we wanted to see whether the digital measures are outperforming or not. And we were able to do that. And thank you for listening. And I would like to acknowledge all the people who are involved in this work from my team, Front Office Sky, Eltoida, and Radar AD. I'm happy to take any questions.